Good day to everyone. I am John Martin Mabansag Navales, BSc E2D in course subject Highway and Railroad Engineering. So today, my report is about Chapter 3, Geometric Design for Highways and Railways. Under Chapter 3 of Geometric Design for Highways and Railways, we have 8 subtopics. Those are number 1, design requirements for highways and railways. Number 2, highway surveys and location. Number 3, geometric design and highway facilities. Number 4, highway drainage. Number 5, horizontal alignment. Number 6, vertical alignment. Number 7, super elevation. And number 8, earthworks. But for today, I will be discussing only for 3.1 to 3.3 as part 1 of my report. 3.1, design requirements for highways and railways. So what are the designs requirements for highways? It says that it should be noted that roadway design criteria and technology is a rapidly changing field of study. So therefore, it is dynamic. Then, the fact that the new design values are presented for updated herein does not imply that existing highway conditions are less safe. So in fact, that there are many technologies or transportation devices that is upgrading or developing due to the advance of technology nowadays. So therefore, we need to consider also our design requirements in highways that will fitted in the different transportation devices to be used in that highway to be designed. Under design requirement for highways, there are 3 subtopics. Number 1, design exemptions. Number 2, design waivers. And number 3, design variants. For design exemptions, a design exemption is required whenever the criteria for certain controlling criteria is specified for the different categories of construction projects are not met. So there are a lot of different construction projects that nas that that does not meet the categories or the requirements. So in this slide, the final approval of road design exemption must be signed by the district engineer and the signature authority cannot be neglected. So this is under the engineer. So there are 4 examples that needs to be included in the design exemptions. Number 1, Director of Transportation Planning and Development. Number 2, Director of Construction. Number 3, Director of Operations Traffic. And Area Engineer. Sorry. Next, project categories will have controlling criteria that dictate a design exemptions. Those are the following: new location and reconstruction projects, resurfacing, restoring, or rehabilitation projects, resurfacing or restoration projects, special facilities, off-system historically significant bridge project, park road projects, and bicycle facilities. Second, for the design waivers, it is defined that the criteria is not met in a non-controlling category, a design exemption is not required. However, variations from the criteria in these cases will be handled by design waivers at the district level. Design waivers will be granted as the district authorities. The complete documentation should be retained permanently in the district projects files and a copy furnished to the design division. Next, design variances. A design variance is required whenever the design guidelines specified in the Americans with Disabilities Act Accessibility Guidelines or ADAAG and the Texas accessibility standards are not met. Design variances should be sent to the Design Division for forwarding to the Texas Department of Licensing and Regulation for approval. Next, design requirement for railways. So have you noticed that there are two different requirements that I have cited? First is for highway only, and now about railways. Okay, next. Geometric design of a railway track includes all those parameters which determine or affect the geometry of the track. These parameters are as follows. Number one, gradients is the track, including grade compensation, rising gradient, and falling gradient. Number two, curvature of the track, including horizontal and vertical curves, transition curves, sharpness of the curve in terms of radius or degrees of curve, cant or super elevations or curves, etc. Number three, alignment of the track, including straight as well as curve alignment. So those three I will be discussed in the latter slides. About there are many types of gradients, and in terms of curvature there is two types of curvature, horizontal curvature and the vertical curvature, and for alignment there are also two, horizontal alignment and vertical alignment. It is very important for trucks to have proper geometric design in order to ensure the safe and smooth running trains at maximum permissible speeds, carrying the heaviest axle load. The speed and axle load of the train are very important and sometimes are also included as parameters to be considered while arriving at the geometric design of the track. So therefore, as an engineer, we need to consider first the safety of the drivers and also the smooth running of trains or to avoid different types of traffics. So next, there are also necessities for geometric designs. Those are follows. Letter A, to ensure the smooth and safe running of trains. Number two, to achieve maximum speeds. Number three, to carry heavy axle loads. Number four, to avoid accidents and derailments due to the defective permanent way. Number five, to ensure that the truck requires less maintenance, and for last, for good aesthetics. In the alignment of railway track and curbs, I will discuss that in the later part of. Okay, what is gradient? Gradients are provided to negotiate the rise or fall in the level of the railway track. A rising gradient is one in which the track rises in the direction of movement of traffic, and in a down or falling gradient, the track loses elevation, the direction of movement of traffic. So the figure illustrates the rising gradient and the falling gradient. Again, a gradient is normally represented by the distance traveled for a rise or fall of one unit. Sometimes the gradient is indicated as percent rise or fall. For example, if there is a rise of 1 meter in 400 meter, the gradient is 1 in 400 or 0.25% as shown in figure 12.1. So it is clearly stated based on the figure that there is a falling gradient of 0.25%. Gradients are provided to meet the following objectives. Letter A, to reach various stations at different elevations. Letter B, to follow the natural contours of the ground to the extent possible. And letter C, to reduce the cost of earthwork. In terms of earthworks, I will discuss that at the last part of my chapter, which is 3.8 earthworks. The following types of gradients are used in the railways. Letter A, ruling gradient. Letter B, pusher or helper gradient. Letter C, momentum gradient. And letter D, gradients in station yards. To elaborate more, it is ruling gradient is the steepest gradient that exists in a section. It determines the maximum load that can carry hold by a locomotive on that section. While deciding the ruling gradient of a section, it is not only the severity of the gradient but also its length as well as its position with respect to the gradients on both sides that have to be taken into consideration. The power of the locomotive to be put into service on the track also plays an important role in taking this decision, as the locomotive should have adequate power to hold the entire load over the ruling gradient at the maximum permissible speed. For pusher or helper gradient, in hilly areas, the rate of rise of the terrain becomes very important when trying to reduce the length of the railway line, and therefore, sometimes gradients steeper than the ruling gradient are provided to reduce the overall cost. In such situations, one locomotive is not adequate to pull the entire load and an extra locomotive is required. For momentum gradient, the momentum gradient is also steeper than the ruling gradient and can be overcome by a train because of the momentum it gathers while running on the section. In valleys, a falling gradient is sometimes followed by a rising gradient. In such a situation, a train coming down a falling gradient acquires good speed and momentum, which gives additional kinetic energy to the train and allows it to negotiate gradients steeper than the ruling gradient. In sections with momentum gradients, there are no obstacles provided in the form of signals, etc., which may bring the train to a critical juncture. Gradients in station yards. The gradients in station yards are quite flat due to the following reasons. Letter A. It provides standing vehicles from rolling and moving away from the yard due to the combined effect of gravity and strong winds. And letter B. It reduces the additional resistive forces required to start a locomotive to the extent possible. It may be mentioned here that generally yards are not leveled completely and certain flat gradients are provided in order to ensure good drainage. The maximum gradient prescribed in station yards on Indian railways is 1 in 400, while the recommended gradient is 1 in 1000. Section, I'm sorry, 3.2 Highways, Surveys, and Location. We are under second subtopic of my chapter. It states that selecting the location of a proposed highway is an important initial step in its design. The decision to select a particular location is usually based on topography, soil characteristic, environmental factors such as noise and air pollution, and economic factors. Why it is said that it is the most important initial step in the design? First, because in designing a highway, we need to consider the availability of materials, its topography or location, soil characteristic if it is okay to construct a highway or railway in that area, and other environmental factors that needs to consider. Principles of highway location. The basic principle for locating highways is that roadway elements such as curvature and grade must blend with each other to produce a system that provides for the easy flow of traffic. at the design capacity while meeting design criteria and safety standards. So what is grade? Grade is just the slope of the highway. That's the grade. Based on the different books that I have read, grades is presented in percent. While the curvature, absolutely, it is the curve of the highway. We're in two different types of curves, horizontal curves and vertical. The highway location process involves four phases. Office study of existing information, reconnaissance survey, preliminary location survey, final location survey. I think this process or these phases are already discussed by Miss Morris in last chapter. But part of the clarity or reiteration, I need to repeat this topic. Okay, first, for the office study of existing information, the first phase in any highway location study is the examination of all available data of the area in which the road is to be constructed. So in this phase, we need to consider the past past conditions or historical events happen in that area for us to know what kind of highway to be constructed or what type of soil is that and others that can give us a hint in constructing highway. Data should be obtained in the following characteristics of area. Engineering, including topography, geology, climate, and traffic volumes. Social and demographic, including land use and zoning patterns. Environmental, including types of wildlife, location of recreational, historic, and archaeological sites, and the possible effects of air, noise, and water pollution. And last, economic, including unit cost for construction and trend of agricultural, commercial, and industrial activity. In the second phase, in reconnaissance survey, the object of this phase of the study is to identify several feasible routes, each within a band of a limited width of a few hundred feet. Factors in reconnaissance survey: terrain and soil conditions, serviceability of route to industrial and population areas, crossing of other transportation facilities such as rivers, railroads, and highways, and directness of route. In preliminary location, we have two different types of feasibility to be considered. First is the economic, and second is environmental. For economic evaluation of each alternative route is carried out to determine the future effect of investing the resources necessary to construct a highway. So, therefore, if we are investing our money or doing this highway project, we need to think or to know the future effect of the project. For environmental evaluation, construction of a highway at any location will have a significant impact on its surroundings. A highway is therefore an integral part of the local environment and must be considered as such. A detailed description of alternatives, the probable environmental impact, including assessment of positive and negative effects, an analysis of short-term impact as differentiated for long-term impact, any secondary effects which may be in a form of charges in the patterns of social and economic activities, Probable adverse environmental effects that cannot be avoided if the project is constructed. Any irreversible and irretrievable resources that have been committed. And last, for final location survey, the final location survey is a detailed layout of the selected route. The horizontal and vertical alignments are determined, and the positions of structures and drainage channels are located. So therefore, in final location survey, it is clearly and firmly finished all the plans in constructing the highway. Location of recreational and scenic routes. The location process of recreational and scenic routes follows the same steps as discussed earlier, but the designer of these types of roads must be aware of their primary purpose. Three additional factors should be considered in the location of recreational and scenic routes as follows. First, design speeds are usually low, and therefore special provisions should be made to discourage fast driving, for example, by providing a narrower lane width. Second, location should be such that the conflict between the driver's attention on the road and the need to enjoy the scenic view is minimized. This can be achieved by providing turnouts with wide shoulders and adequate turning space at regular intervals, or by providing only straight alignments when the view is spectacular. And last, location should be such that minimum disruption is caused to be. Location of highways in urban areas. Urban areas usually present complex conditions that must be considered in the highway location process. In addition to the factors discussed under office study and reconnaissance survey, other factors that significantly influence the location of highways in urban areas includes the connection to local streets, right-of-way acquisitions, coordination of the highway system with other transportation systems, adequate provisions for pedestrians. So why it is said that the urban areas is a complicated to design? Why? Because there are a lot of population or people that needs a service or a transportation in the highway. Next, principles in bridge location. The basic principle for locating highway bridges is that the highway location should determine the bridge location, not the reverse. When the bridge is located first, in most cases, the resulting highway alignment is not the best. The general procedure for most highways, therefore, is to first determine the best highway location and then determine the bridge site. In some cases, this will result in skewed bridges which are more expensive to construct or in locations where foundation problems exist. So therefore, in locating the location of the highway and bridge must be considered because it is not easy to locate the location for highway and also it is not easy to locate the location of bridge. For highway survey methods, highway surveys usually involve measuring and computing horizontal and vertical angles, vertical heights, elevations, and horizontal distances. The surveys are then used to prepare base maps with contour lines and longitudinal cross-sections. Highway surveying techniques have been revolutionized due to the rapid development of electronic equipment and computers. So, in our previous core subject, CE1, Fundamentals of Surveying, that is already discussed. So I don't need to elaborate more about how to compute the angles, how to compute the distance, because that is already done. Highway survey methods. There are three types of highway survey methods: ground surveys, remote sensing, and computer graphs. For ground surveys are the basic location technique for highways. The total station is used for measuring angles in both vertical and horizontal planes, distances, and changes in elevation through use of trigonometric levels. The level is used for measuring changes in elevations. So, survey equipments of surveys are the following: total station, electronic distance measuring devices, level measuring tape. For remote sensing is the measurement of distances and elevations by using devices located above the Earth, such as airplanes or orbiting satellites using global positioning systems. And for computer graphics when used for highway location is usually the combination of photogrammetry and computer techniques with the use of mapping software, line styles, and feature tables, objects, and photographic features can be recorded digitally and stored in a computer. For subtopic 3.3, Geometric Design and Highway Facilities. In this subtopic, there are a lot of things to consider. So I will discuss it here. Geometric Design and Highway Facilities. Geometric design deals with the dimensioning of the elements of highways, such as vertical and horizontal curves, cross-sections, truck climbing lanes, bicycle paths, and parking facilities. The American Association of State Highway and Transportation Officials serves a critical function in developing guidelines and standards used in highway geometric design. The membership of AASHTO includes representatives from every state highway and transportation department in the U.S. as well as the Federal Highway Administration. Factors influencing highway design are the following: functional classification, design hourly traffic volume and vehicle mix, design speed, design vehicle, cross-section of the highway such as lanes, shoulders, and medians, presence of heavy vehicles on steep grades, topography of the area that the highway traverses, level of service, available funds, safety, and social and environmental factors. Highway functional classifications. Highway are classified according to their functions in terms of the service they provide. Within the classification of urban and rural highways are categorized in the following groups: principal arterials, minor arterials, major collectors, minor collectors, local roads and streets. Freeways are not listed as a separate functional class since they have generally classified as part of the principal arterial system. However, they have unique geometric criteria that require special design considerations. For functional system of urban roads comprise highway facilities within urban areas as designated by responsible state and local officials to include communities with a population of at least 5,000 people. This system of highways serves the major activity centers of the urban area and consists mainly of the highest traffic volume corridors. So as you can see in the picture, the legend are the following. There is Arterial Street, Commercial Area, Local Street, Collector Street, and Public Area. Urban Minor Arterial System. Streets and highways have interconnect with and augment the urban primary arterials are classified as urban minor arterials. Urban collector street system. The main purpose of streets within the system is to collect traffic from local streets in residential areas or in CBDs and convey it to the arterial system. Urban 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 local street system. This system consists of all other streets within the urban area that are not included in the three systems described earlier. The primary purposes of these streets are to provide access to abutting land and to the collector streets. Through traffic is discouraged on these streets. Functional system rural roads. So what are the difference between urban and rural? So urban, it is a location wherein there are many people or having a big population than the rural areas. Highway facilities outside urban areas comprise the rural road system. These highways are categorized as principal arterials, minor arterials, major collectors, minor collectors, and locals. So as you can see in the picture, based on the legend, there is cities and towns, village, arterials, collectors, and locals. So as you can see, the cities and towns are located nearly at the end part or the outside part of the picture because this is a rural roads. Therefore, there is limited population. Rural principal arterial system. This system consists of a network of highways that serves most of the interstate trips and a substantial amount of intrastate trips. Rural minor arterial system. This system of roads augments the principal arterial system in the formation of a network of roads that connects cities, large towns, and other traffic generators such as large resorts. Rural collector system. Highways within the system carry traffic primarily within individual countries, and trip distances are usually shorter than those on the arterial roads. This system of road is subdivided into major collector roads and minor collector. For rural major collector system, routes under this system carry traffic primarily to and from country seats and large cities that are not directly served by the arterial system. The system also carries the main intra-country traffic. For rural minor collector system, this system consists of routes that collect traffic from local roads and convey it to other facilities. One important function of minor collector routes is that they provide linkage between rural hinterland and locally important traffic generators such as communities. For rural local road system, this system consists of all roads within the rural area not classified within the other systems. These roads serve trips or relatively short distances and connect adjacent lands with the collected roads. So, highway design standards. Selection of appropriate set of geometric design standards is the first step in design of any highway. This is essential because no single set of geometric standards can be used for a highway. So there are a lot of standards to be considered in designing a highway. So therefore, we are expected to know or to familiarize the different design standards. First, design hourly volume. The design hourly volume, or DHV, is the projected hourly volume that is used for design. This volume is usually taken as a percentage of the expected average daily traffic, or ADT, on the highway. As you can see in the figure, relationship between peak hour and annual average daily traffic on rural highways. And the upper graph, it is the exit at 15% of location. The middle graph, road with average fluctuation in traffic flow. And the third graph, exceeded at 85% of location. Design speed. Design speed is defined as the selected speed to determine the various geometric features of the roadway. Design speed depends on the functional classification of the highway, the topography of the area in which the highway is located, and the land use of the adjacent area. So there are different speeds to consider in designing a highway. The table states or dictates the minimum design speeds for various functional classifications. So, in the right side is the speed in miles per hour, and in the left side is for the class or types of highways to be designed. Next, design vehicle. A designed vehicle is selected to represent all vehicles on the highway. Its weight, dimensions, and operating characteristics are used to establish the design standards of the highway. The following guidelines apply when selecting a designed vehicle. First, when a parking lot or a series of parking lots are the main traffic generators, the passenger car may be used. Second, for the design of intersections at local streets and park roads, a single unit truck may be used. And last, at intersections of state highways and city streets that serve buses with relatively few large trucks, a city transit bus may be used. The following guidelines apply when selecting a design vehicle. At intersections of highways and low-volume country highways of township, local roads with less than 400 ADT or average daily traffic, either an 84-passenger large school bus 40 feet long or a 65-passenger conventional bus 36 feet long may be used. The selection of either of these will depend on the expected usage of the facility. At intersections of freeway ramp terminals and arterial crossroads, and at intersection of state highways, at industrialized streets that carry high volumes of traffic, the minimum size of design vehicles should be WB20. Collector roads. For medians, a median is the section of divided highway that separates the lanes in opposing directions. The width of a median is the distance between the edges of the inside lanes, including the median shoulder. The function of a median include providing a recovery area for out-of-control vehicles, separating opposing traffic, providing stopping areas during emergencies, providing storage areas for left turning and U-turning vehicles, providing refuge for pedestrians, reducing the effect of headlight glare, providing temporary lanes and crossovers during maintenance operations, or slopes on the roadside. They also have been used to shield pedestrians and property from the traffic. For curbs and gutters, curbs are raised structures made of either Portland cement concrete or bituminous concrete that are used mainly on urban highways to delineate pavement edges and pedestrian walkways. Curbs are also used to control drainage, improve aesthetics, and reduce right-of-way. So in designing curbs and gutters, there are guides to consider also in a AASHTO guidelines about dimensions and other requirements. For guardrails are longitudinal barriers placed on the outside of sharp curves and at sections with high fields. Their main function is to prevent vehicles from leaving the roadway. So therefore, guardrails are used to minimize accidents. Sidewalks are usually provided on roads in urban areas but are uncommon in rural areas. Nevertheless, the provision of sidewalks in rural areas should be evaluated during the planning process to determine sections of the road where they are crossed slopes. Pavements on street sections of two-lane and multi-lane highways without medians are sloped from the middle downward to both sides of the highway, resulting in a traverse or a cross slope with a cross-section shape that can be curved, plane, or a combination of. So here are the typical highway curves. There is vertical curve and sloping curves. As you can see, a vertical curve having 8 in 6 inches to 8 inches height and 6 inches width at top and 7 inches width at the bottom. For the sloping curves, there are 6 types. Those are the following presented. Basic cross-slope arrangements for divided highways. Letter A, each pavement slopes two ways. Letter B, each pavement slopes one way. So it is clearly stated in the figure. Side slopes. Side slopes are provided on embankments and fail to provide stability for earthworks. They also serve as a safety feature by providing a recovery area for out-of-control vehicles. When being considered as a safety feature, the important section of the cross slope are the hinge point, the foreslope, and the two of. Based on the figure, it is the designation of roadside regions. There is hinge point, foreslope, toe of slope, ditch bottom, and back slope, and traffic lane. Traffic. Again, there is another table, guide for earth slope design. There is a given ratio for flat or rolling, moderate, steep, and steep. Maximum highway grades. Again, grades is the slope. The selection of maximum grades for a highway depends on the design speed and the design vehicle. It is generally accepted that grades of 4 to 5% have little or no effect on passenger cars, except for those with high weight horsepower ratios such as those found in compact and subcompact cars. As the grade increases above 5%, however, speeds and the passenger cars decrease on upgrades and increase on downgrades. So if the highway is increasing in slope, so therefore the speed of the vehicle decreases. And if the slope is decreases, the speed of the vehicle increases. So there is an inversely proportional relationship between the highway grades and the speed of the vehicle. Design of the alignment. The alignment of highway is composed of vertical and horizontal alignments. The vertical alignment includes straight tangent highway grades and the parabolic curves that connect these grades. The horizontal alignment includes the straight tangent sections of the roadway and the circular curves that connect their change in direction. So I have stated that there are two types of alignments, the vertical and the horizontal alignments. I will discuss that in the later part of my report. So based on the table, these are the following recommended maximum grades in designing a highway. There is a table for rural collectors, urban collectors, rural arterials, rural and urban freeways, and urban arterials. For vertical alignment, the vertical alignment of a highway consists of straight sections known as grades connected by the vertical curves. The design of the vertical alignment therefore involves the selection of suitable grades for the tangent sections and the appropriate length of vertical curves. So there are types of vertical curves. As you can see, there are type 1, type 2, type 3, and type 4. The different letters presented in the different types of vertical curves as given below. G for grades of tangents, A for algebraic difference, A for length of vertical curves, PVC for point of vertical curve, PVI for point of vertical intersection, PVT for point of vertical tangent. So the difference is that in type 1, the G1 is positive while the G2 is negative. In type 2, the G1 is positive and the G2 is positive, and the other one is the G1 is negative and the G2 is also negative. For type 3, the G1 is negative and G2 is positive, and for type 4, the G1 is negative and the G1 is negative also, and G1 is positive and G2 is positive. In this type of curve, by the way, I haven't included different types of computations here in this part because we are already done this in our surveying class. So those are the following curves presented. Minimum length based on SSD criterion. The headlight SSD requirement is based on the fact that sight distance will be restricted during periods of darkness, whereas during daylight periods, sight distance is unaffected by the subcurve. So in short, it is just considering that the light should see the other vehicle passing forward or towards that vehicle. This is in consideration for the safety of, again, this minimum length based on SSD criterion. It is to determine the safety of the vehicles, considering the length. Minimum length based on a comfort criterion. The comfort criterion is based on the fact that when a vehicle travels on a subvertical curve, both the gravitational and centrifugal forces act in combination, resulting in a greater effect than on a crest vertical curve, where these forces act in opposition to each other. Several factors such as weight carried, body suspension of the vehicle, and the tire flexibility affect comfort due to change in vertical direction, making it difficult for comfort to be measured directly. It is generally accepted that a comfortable ride will be provided if the radial acceleration is not greater than 1 feet per second squared. Horizontal alignment. The horizontal alignment consists of straight sections of the road known as tangents connected by the curves. The curves are usually segments of circles which have radii that will provide for a smooth flow of traffic. The design of the horizontal alignment entails the determination of the minimum radius determination of the length of the curve and the computation of the horizontal offsets from the tangents to the curve to facilitate locating the curve in the field. Special facilities for heavy vehicles on steep grades. Special facilities for heavy vehicles on steep grade. Climbing lanes. A climbing lane is an extra lane in the upgrade direction for use by heavy vehicles whose speeds are significantly reduced by the grade. A climbing lane eliminates the need for drivers of light vehicles to reduce their speed when they encounter a heavy, slow-moving vehicle. Emergency escape ramps. An emergency escape ramp is provided on the downgrade of the highway for use by a truck that has lost control and cannot slow down. A lane is provided that diverges such that when a vehicle enters the escape ramp, its speed is gradually reduced and eventually its bicycle facility. The bicycle, a viable alternative mode of transportation, is popular particularly in urban and suburban areas as a means to travel within the community both for recreation and necessary travel. So the figure illustrates the basic types of emergency escape ramps. Letter A, that is for sand pile. Letter B for descending grade. Letter C, horizontal grade. And letter D for ascending grade. Bicycle lanes. A bicycle lane is that part of the street or highway specially reserved for the exclusive or preferential use of bicycle riders. Bicycle lanes can be delineated by stripping, signing, or paving markings. These lanes should always be in the direction of traffic. So the next figure illustrates the typical bicycle lanes cross sections. Letter A for curb street with parking. Letter B curb street without parking. And letter C street or highway without curb or gutter. Bicycle paths. Bicycle paths are physically separated from automobile traffic and may be used exclusively by a cyclists or possibly with pedestrians. The design criteria for bicycle paths are similar to those for highways with criteria governed by bicycle operating characteristics. Important design considerations for a safe vehicle path include the path width and design speed as well as the horizontal alignment. So the next figure illustrates the channelization of bicycle lanes approaching motor vehicle right turn only lanes. For the upper left, that is for right turn only lane. For upper right, that is only for parking lane becomes right turn only lane. For lower left, optional double right turn only lane. And the last, in the bottom right, right lane becomes right turn on the lane. Width of vehicle paths. A typical layout for a bicycle path of a separate right of way is shown in figure 15.30. The minimum recommended width is 10 feet for two-lane paths, a 5 feet for one-way paths. The width for the two-way path may be 8 feet under the following conditions. 1. Low vehicle volumes at all times. Number 2. Vertical and horizontal alignments are properly designed to provide frequent safe passing conditions. Number 3. Only occasional use of path by pedestrians. And number 4. The absence of maintenance of vehicles. So the next figure illustrates the path of separated right-of-way. There's a width of 5 or 8 feet width that have 2% grade minimum, and for the left and right side there is 2 feet minimum for graded. Parking facilities. The geometric design of parking facilities involves the dimensioning and arranging of parking bays to provide safe and easy access without restricting the flow of traffic on the adjacent traveling lane. Design on on-street parking facilities. On-street parking facilities may be designed with parking bays parallel and inclined to curb. Figure 15.33 on the next page illustrates the angles of inclination commonly used for curb parking and the associated dimensions for automobiles. The number of parking bays that can be filtered along a given length of curb increases as the angle of inclination increases. So the next illustration is street parking used for various parking configurations. So there are given lengths for parallel, for 30 degrees, for 45 degrees, for 60 degrees, and for 90 degrees. N is the number of spaces and L is the curb length. Next, design of off-street parking facilities, surface car parks. The primary aim in designing off-street parking facilities is to obtain as many spaces as possible within the area provided. Figures 15.34 and 15.35 show different layouts that can be used to design a surface parking lot. The most important consideration is the layout should be such that parking a vehicle involves only one distinct maneuver without the necessity to reverse. So the figure for parking stall layout, it is clearly stated in the figure. There is a 23 feet clear aisle, 15 feet, 16 feet, and 22 feet. Design of off-street parking facilities for a garage. Parking garages consist of several platforms supported by columns which are placed in such a way as to facilitate an efficient arrangement of parking bays and aisles. Access ramps connect each level with one above. The gradient of this ramp is usually not greater than 1:10 on straight ramps and 1:12 on the center line of curved ramp. So the figure illustrates the herringbone layout on parking stalls in an on-surface lot. So that's all for today. Thank you for listening.